Well, hello, I'm going to work through some tutorial problems that are connected with our journey into number theory and the various sections and various recordings. So we're beginning with some classical number theory, and the first exercise here is to find all integers n, or positive integers n, so that 5n is 12, and all the positive integers such that 2n is equal to 5n. And also show that 5n equals 14 is impossible. And here's the work solution for that. So we start off with, we're going to look at 5n equals to 12. So I'm just going to play around a bit. I'm going to factorise 12 as 2 squared be 3 or 6 be 2 to help in the calculations. And I can pick some values immediately. N equals 13, because 13 is prime, then we can get n as 13 as one of the solutions of 5n as 12. And looking at this one here, because 6 plus 1 is 7 is prime and 2 plus 1 is 3 is prime, using the multiplicative nature of phi, then n equals 7 times 3 is 21 will be a solution. Now, once we've got 13, we know that 5(2) is 1, so we can double this. We get 526, n equals 26 as a solution. And also we can take our 21, which is odd, and I can double it and get 42. That's also going to be a solution. So we've got so far 4 of these, but there are more. And one way of getting our hands on the rest of them is to start looking at phi of various factors of for factors here. So we get 5(3) is 2, 5(4) is 2, 5(5) is 4, 5(6) is 3. So I'm looking for numbers here that are factors of 12. And I don't need to go beyond 9 here. So I now just look through here and see if I can find what combinations of these are going to multiply to give me the 12. So in particular, and they've got to be relatively prime, so in particular 5, 4, 4 and 9, 6 2's give me 12. 4 and 9 are relatively prime, so 9 4's are 36 will be a solution. And I look through and I can see that 6 and 7 and 4, I can take this one here with this one here. 7 and 4 relatively prime, 6 2's are 12, and so 7 4's are 28 also works, and there are no other combinations here that you can multiply together where the numbers in the brackets are relatively prime. So they are the solutions: 13, 26, 42, 36, 28. For the second one, we want 5(2n) to be equal to n. Well, if n is odd, then immediately we have 5(2n) is 5(2) times 5n is 5n, so any odd number will make this work. Now, if n is even, then with an even number, one of the tricks you can do in number theory with even numbers is you can factor out as many 2's, so the alpha has to be at least 1 if n is even. You can factor out all the 2's and you're left with an odd number. And now, because these are relatively prime, you can apply the multiplicative nature. So 5(2n) then will be 5(2) to the alpha times 5m. 5(2) to the alpha is 2 to the alpha plus 1 minus 2 to the alpha times 5m. So that means, and this is supposed to equal 5n, and 5n is 2 to the alpha minus 1 minus 2 to the alpha minus 2 to the alpha minus 1 times 5m. And so equating these, cancelling out the 5m, we get this expression, which doesn't look very happy. And indeed, if you divide everything through by 2 to the alpha minus 1, you get this equation, which is impossible. In other words, you can't have n even with 5(2n) equaling 5n. So a conclusion is that 5n equals 5(2n) if and only if n is odd. Finally, if 5n is 14, which is 2 times 7, then using the table we had above in part A, you can see that there are no possible products that will multiply to give you the 14, and so there are no such n's. Question 2 of the problems says we want now to suppose that m and n are relatively prime positive integers, and we want to show that m to the 5n plus n to the 5m is congruent to 1 mod mn. Now, by the way, you might like to try these yourself beforehand and then before looking at the solutions, but the solutions are here for you to check and compare what you did to what I do. So here is the solution of this. So we're given that m and n are relatively prime. We've got a GCD of 1. We're asked to show this congruence. So it looks like we're going to need Eulers Theorem, so I write that down, just brainstorm a bit. So for Eulers Theorem, m to the 5n is 1 mod n, and n to the 5m is 1 mod m. And I can just take this minus this, which is going to be 0 mod n, and this minus this, which is 0 mod m, and if I multiply those together, then I'm going to get 0 mod mn. And if we simply expand all this out, remembering that any term with mn in it is going to be 0, the result will follow immediately. Question 3 is to show that we can write our 5n as n times this product. This sort of very basic Euler type product of the product of p divides np is prime 1 minus 1 over p. This one is very easy to do. You might like to try that first before seeing the solution. Here is the worked solution to it. All we do is we simply take our unique canonical factorisation of n, which we can write as p1, alpha 1 and so on, where these PRs are all primes. And we can then take a phi of each of these and then take a product. So phi of p sub I to the alpha I is just p sub I to the alpha I minus p sub I to the alpha I minus 1, and we take a product of all of those. And out of this I can take a pi to the alpha I going from 1 up to r. So I'm going to get this one here, and the bits left, I'm going to get 1 minus 1 over each of these primes, and that's it then. And we can just rewrite that. This is the n we started with, and I can rewrite this product as the product over the prime factors of n, 1 minus 1 over p. Question 4, slightly more tricky one, but there's a little hint there to help us. So we want to prove that the sum of the numbers, so we've got some n, we think of n as being given, and we want to take all the integers that are relatively prime to n, and we're going to add them all up. So we're taking a sum here of all the integers that are relatively prime to n, and less than it. And the answer turns out to be, rather lovely formula, it's a half n phi n. And we're given a hint to look at u sub n, which is x1 up to 5n. These are the numbers that are relatively prime to n, and there will be phi n of these. So we're going to number them in this way, and then also note that this can also be written as we can take n minus each of these, and we'll get the same set but in some different order. Well, here's the solution of this. So here's the question, and I take their hint, and we're told that these are identical as sets, but the elements written in a different order. So that means I can take the sum of these numbers, which is what I'm looking for, and then that will equal the sum of these numbers. So the sum that I'm looking for, the sum of the numbers that are relatively prime to n, is just going to be the sum of all these xi's up to x5n, and that's got to equal the sum of the ones in the other set. And of course that's going to give me n times, I'll get phi n lots of n in this one here, and I'm going to get minus the sum I had on the other side. So twice the sum I'm looking for is just n5n, and now you divide by 2. So that was a fairly easy one. Question 5, I'll just put in here quickly. It says you want the number of fractions r over s, r and s are positive, and r less than s and less than n, and you want r and s to be relatively prime. So that is, you fix n and you take all the fractions whose denominators are less than n, all the fractions where the numerator and denominator are relatively prime, and you want to know how many such ones there are. And that's fairly easy, because you're just going to say, well, if you've got a denominator of if you've got r is equal to 1, s has got to equal 2, so the number of fractions with denominator relatively prime to 2 is going to be 5, 2. Then the number of fractions with denominator 3, where these are relatively prime, is going to be 5, 3. And so obviously you just take a sum of phi k, k equals 2 to n. So that was a fairly easy problem. Question 6 is, we take g is a primitive root mod p, where p is an odd prime, and we want to show that we can take any, if we take this g, raise it to any power that's relatively prime to p minus 1, then that number is also a primitive root, and then we're going to use that to compute all the primitive roots for p is 13 and 17. But that's a very nice exercise, because it gives us a way of, once we've got one primitive root, it gives us a way of constructing all the others. So for 6a, we're starting off with g is a primitive root mod p, p is an odd prime, and we want to show that this is also a primitive root. I'll use pr for primitive root. So I'm going to take this g to the k, and I'm going to say, well, if it's congruent to, if I raise this to some power alpha to get 1, well, then we know then that k times alpha is 0 mod p minus 1. So this has to be a factor of p minus 1. In other words, I'm trying to find the order of h to the k. So if I can raise this to the power alpha and I get 1, then k alpha has to be 0 mod p minus 1. We were also given that the GCD of k and p minus 1 is 1. These are relatively prime. So that means any number which, that will therefore mean that we can cancel the alpha. So k will have an inverse mod p minus 1, and that means alpha is 0 mod p minus 1. Well, alpha is either, if alpha is not 0, then and it's 0 mod p minus 1, then alpha must equal p minus 1. And that means g to the k has order p minus 1, so it's a primitive root. Now we can use that to find all the primitive roots modulo 13. So we take g as equals 2 as a primitive root mod 13. That's fairly easy to prove. You just have to check 13 minus 1 is 12, so you have to check that 2 squared, 2 cubed, 2 to the 4th, and 2 to the 6th are not 1 mod 13, and they're not, so g equals 2 as a primitive root. So you get all the primitive roots by simply raising this to any power that is relatively prime to 12. So that's 1. You can't use 2, 3, or 4. You can use 5. You can't use 6. You've got 7. You can't use 8 or 9. You get 11. And when you simplify these, you end up with these 4 numbers, plus or minus 2, plus or minus 6. For p equals 17, 2 is not a primitive root, because obviously 2 to the 4th is minus 1. So 2 to the 8th is going to be 1, so it's not a primitive root. However, 3 happens to be a primitive root, which is nice. And so you can get all the primitive roots by taking 3 raised to any power relatively prime to 16. So 1, 3, 5, 7, all the way up to 15, the odd numbers. And when you evaluate those, you get these 8 numbers, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 7. Question 7 asks us to show that if we consider a prime p of the form 4t plus 1, if a is a primitive root mod p, if and only if minus a is a primitive root mod p. So we're going to do that by just checking through. So we've got p is of the form 4t plus 1 is prime, a is a primitive root mod p, and I'm going to consider minus a to the k, and we want to show that this k is, which would be the order of minus a, is actually equal to p minus 1. So I can split this up into minus 1 to the k, a to the k, and that's got to be congruent, and that's congruent to 1. So I'm assuming that this is congruent to 1. So if k is even, then this is 1, and so a to the k is 1, and that means k this is p minus 1. So I should really say a is a primitive root, consider the k where k is the order of minus a. So if k is the order of minus a, then this is congruent to 1. If k is even, then it's got to be p minus 1, so minus a is a primitive root. Now if k is odd, then this becomes a minus, so you get minus a to the k is congruent to 1 mod p. Now you can square both sides, and you get a to the 2k is 1 mod p, and yet a to the k is not, so 2k has to be p minus 1. Now that tells me that k is odd, so I can write k is 2l plus 1. And now I look at p minus 1, plug that back into here, I get p minus 1 is 4l plus 3, which means p is prime congruent to 3 mod 4, but that's impossible because p was a 1 mod 4 prime. And that tells me then that minus a is a primitive root, and for the converse you just replace a with minus a and you'll get the other way around. Question 8. We want to find the number of primitive roots in Z13, Z101 and U12. And second part says if Q is a prime of this shape, that is if it's a Fermat prime, then Z sub Q has that many primitive roots. So that's just a very simple little exercise there, because we know that the number of primitive roots in ZP is 5p minus 1. So in Z13 there are 5 of 12, and 5 12 is 4 primitive roots. 101 is a prime, so there are 5 100, which is 40 primitive roots mod 101. Now in U12 there are none, since each element has order at most 2. If you write the elements of this out, you get 1, 5. 5 squared is 1, it's got order 2. 7 squared is 49, which is 1 mod 12, that's got order 2. And 11 is minus 1 squared, also is a 1, so that's got order 2. So none of the elements, since there are none, since each element has order at most 2. The number 1, of course, having order 1. For the second part, we take Q to be a prime of this form. These are called Fermat primes. There are not many known. And again, there are 5 Q minus 1 primitive roots. That's 5 2 to the 2p. We know how to work this out. It's 2 to the 2p minus 2 to the 2p minus 1. And we can factor out a 2 to the p minus 1 out of that, and we just get that expression. For question 9, we're going to use the existence of a primitive root modulo p to prove Wilson's theorem. And the second part says, suppose p is prime, we want to prove that if p minus 1 is not a factor of k, then when I take the sum of the kth powers of these, then this is 0 mod p. Now interestingly, the converse of this, which would conclude the primality of p, So that is, if this is true, then P is prime, is, as far as I'm aware, still an unsolved problem. So this is a rather interesting little example here. So here's a little proof of this result. We want to prove Wilson's theorem firstly. So if G is a primitive root mod P prime, then P minus 1 factorial, we'll just write out what it means. Now, because it's a prime, every prime has a primitive root, so each one of these elements in this product here is a power of the primitive root, so I can write it as a product in some order. These won't be in the same order, of course. The G to the P minus 1, in fact, is 1. But they're in some order, and then I can just use the index laws and add these all up. And this is a simple arithmetic series, so it's a half P minus 1. Now P minus 1 is even, so the 2 goes into that, so that's an integer, of course. And I can rewrite that as G to the P minus 1 over 2 to the P. Now G to the P minus 1 over 2 is minus 1, because G is a primitive root. And minus 1, P is an odd prime, so the minus 1 to the P will be minus 1 mod P. If P happens to be 2, then I think the result still holds anyway, trivially. And there's Wilson's theorem. The second part said if P minus 1 is not a factor of K, then we take G to be a primitive root, and we're looking at this sum here. And again, we can replace each of the numbers 1, 2 up to P minus 1 by some power of the primitive root. It's either going to be G or G squared or G cubed. So again, in some order, not the same order as here, but in some order, each of these elements is just a power of G. Perhaps I should have written this as G squared to the K and so on for consistency. I can factor, and this one here, of course, again as a geometric series, I can factor out a G to the K and then sum this as a geometric series. So it's going to be this multiplied by the inverse of this. Now, the fact that P minus 1 is not a factor of K tells me that G to the K can't be 1 mod P, and so this inverse exists. You've got to worry about that, whether this has any meaning, but it does because of this condition. And that means then that this expression here is 0 modulo P, because this is just G to the P minus 1 is 1, 1 to the K is 1, minus 1 is 0 mod P, and that finally tells me that my sum then is congruent to 0 mod P. Final one for this section, question 10. If A has order 3 mod P, P is a prime greater than 5, we want to show that 1 plus A has order 6. 1 plus A has order 6. And here is the solution to that one, and this will be the last one in this recording. So if P is a prime bigger than 5, A's got order 3. That means A cubed is 1 mod P. Now you can factorise that in the obvious way. It's a sum of 2 cubes, and A is not 1 because 1 doesn't have order 3, so that means this must be 0 mod P. So I can take the minus A squared on the other side, and I can write this down. And so now I want to start squaring now. So A plus 1 squared is going to be minus A to the 4th, but A to the cubed 1, that's minus A, and that's not 1. A plus 1 cubed is minus A to the 6th, which again is congruent to minus 1, which is not 1. But I can now square both sides, and A plus 1 to the 6th is 1. So A plus 1 has order 6. And they are the relevant problems for the first section, or the first recording.